Hello, this video we will discuss about example of how to calculate the entropy change if the process is constant pressure. So for example here, there's a piston cylinder and it is actually constant pressure. So P1 equal to P2 and it's a constant value. Then inside this piston cylinder, it's water. And initial pressure is 20 psi. P1 is 20 psi. And initial temperature is 70 Fahrenheit. And the mass of water is 3-pound mass. Okay, and then the water is now heated at constant pressure by adding, so there's a heat coming, and this Q is given is as 3450 BTU. And we are asked to find what's going to be the entropy change for this situation. We need to find delta S. What's that equal to? So how do we go about this one? First, you want to find the delta S. We need to know final and initial respectively, right? I think that would be a good way to start. So can we find S1 first? So for S1, we know the pressure. For state 1, we know the pressure is 20 psi. And T is 70. So we need to go to our pressure table. And I believe this time we need to look at a total different table since this is a US system. Okay. So this is water, 20 psi. So table A5, E at 20 psi. And we realize the temperature at the time, temperature at this 20 psi is equal to 227.92 Fahrenheit. And our temperature is way less than that value. Right, our temperature is 70 and this is 227. That tells us this is a compressed liquid. If it is compressed liquid, we're going to go to the right table, our table A7. At our table A7, we realize the lowest pressure they have here for this particular textbook is 500 psi, and our pressure is 20 psi. However, we're not stuck, right? If it does not show up at the compressed liquid table, we can approximate. And we approximate using table A4, the temperature table. Table A4E. So we're trying to find S. So this S1 is going to be approximate equal to the saturated liquid at this temperature, 70 Fahrenheit. So let's go to table A4. Table A4 at 70 Fahrenheit. We can find our S value. And our S value is this one, right? Oh. It's 0.07459. So that is our initial state entropy. And the unit is BTU per pound mass per ranking. Okay, So knowing that now, we can go ahead trying to find S2. Do we have two properties to find the entropy? What's the first property we know? This is constant pressure process, so we do know P2 is going to be equal to P1, and that's going to be equal to our 20 psi. But we don't have any other information anymore, right? However, they give us this heat transfer. Then we're going to use our first law of thermodynamics, which is conservation for energy. Now, this is a closed system. Closed system means only energy can transfer in and out, but mass does not, right? So first law for closed system, we know for constant pressure process, we know this equation right away, which is our Q, heat transfer, is equal to delta U plus work others. Okay. Why do we use this one? Because it is a constant pressure, right? Oh, this is a constant pressure process, right? So I made a mistake. If it's a constant pressure process, it's going to be Q equal to delta H, my bad. If it's a constant volume, then it's going to be Q equal to delta U plus work others. So for this one, there's no other type of work. We didn't see other than boundary work, right? There's no other type of work. There's no electrical resistor going through. There's no shaft, paddle wheel turning on. So other type of work here is 0. And we also know the heat transfer is 3450 BTU. And we know the mass, right? And we know delta H is going to be equal to final minus initial. Okay, now let's continue digging into this. Our mass value is 3 pound mass. And do we know H2? We don't. We're trying to find our second property, right? But we do know, can we find H1? Yeah, we can go find H1 even though we didn't have a foresight earlier to find H1. But now we need go back to find our H1. So just like how we did finding our S, our entropy, we're going to find our enthalpy, H1. Since this is a compressed liquid for state 1 and our table does not show up, does not have tabular data for this particular 20 psi, then we remember we approximate, so we're going to use saturated liquid at this particular temperature, 70 Fahrenheit. So going back to the same table, which is table A4E, we can find our H value. HF is 38.08. And that's BTU per pound mass. And that comes really helpful now, right? So we know this is 38.08. That's our H1. Also, we use this first law, energy conservation. We can solve H2. That will be our second property. So when you solve this, our H2 come up around to be 1188.1 BTU per pound mass. Okay. So knowing that now, I'm changing the color because the green is just for H, right? And now let's go back to our second state. We know P2, it's a constant pressure, so it's equal to P1 as 20 psi. We also know the second property we just calculated H2, it's 1188.1 BTU per pound mass. So knowing these two properties, we're going to table A5E because pressure is given. At 20 psi, how is our H compared to HF and HG. So Hg here at 20 psi, it's 11. It's this value, right? It's 1156.2. And our H2 value is even greater than Hg. That means this is a superheated vapor. Since we know this is a superheated vapor, we're going to go to the right table, table A6E, trying to find our S2, right? So our H2 value is right here, 1188.1, and our pressure is 20 psi. So let's take a look. At 20 psi milli table, our H column, let's look around here, and it's 1188. And so that's between those two rows, right? It's between those two values. And we want to find corresponding S. So we need to get those two values for S out. Now let's list it. So this is our H column, this is our S column, and it's 1181.9. Corresponding S is 1.7679. And for H is equal to 1201.2. Corresponding is 1.7933, and our H2 value is 1188.1. It's in between those two values. We want to find out what's the corresponding entropy for that. So in order to solve this, this is not new to us. We need to find our linear interpolation. So for linear interpolation, we're going to write down our equation. So we're using 1.7933. So here I'm using delta S over delta H minus 1.7679. Then corresponding H is 1201.2 minus 1181.9. Then how about right-hand equation? We'll have S will be 1.7933 minus the S you're solving. Then corresponding H for this S value is 1201.2 minus the corresponding H value for that is 1188.1. And when we solve that, we get our S value. So here I will just look at the answer here. It's 1.7761, which is in between those two values, right? Okay. And that gives us BTU per pound mass per ranking. So knowing that now, we can find out our last step, which is delta S, the entropy change for this refrigerant. Final minus initial. Final is 1.7761, and our initial is way back. We found out this S1 being a compressed liquid, and we approximate it using the saturated liquid at that temperature. It's 0.0749. And we have our answer. But be aware, this problem gives us the mass. So we likely they want us to find actual entropy. So we're going to times mass. And this mass is 3 pound mass. Okay. Then we calculate, the answer is 5.105. It's BTU per pound mass. That's our entropy change for this constant pressure process. This is a great example. We use so many O scales, right? Because it's constant pressure, and we used the first law of conservation. Because it's constant pressure, so Q is equal to delta H, and we find our H value, then we also used approximation. We also use linear interpolation. Okay, so that's good. I'll see you at the next one. Goodbye now.